Washington State is quickly becoming like the Silicon Valley when it comes to commercial space companies and programs. And Starfish Space is one of those. They're doing something pretty amazing, but they had a little bit of a rough start to their initial testing program with their Otter Pup program that they're going to be working on here. And joining us is Starfish Space co-founder Trevor Bennett. Trevor, appreciate you joining us. Why don't you start by telling us a little bit about the Otter Pup program and what you hope to achieve here?
Yeah, thank you for the intro, Ryan. I appreciate you having me on today. A little bit about what Starfish Space is and why we have this spacecraft called the Otter Pup in orbit. Starfish Space was founded back in 2019 by myself and my co-founder, Austin, with the ambition and dream of creating a satellite and a service that could grab and move other satellites around. And that is for life extension, debris removal, recycling, manufacturing, assembly. All of these things can be true if you can do that grab and move maneuver. Specifically for us, we, in our technology development path as both a startup and kind of pioneering some new technology in our own right, needed to go test those key aspects on orbit. And for us, there were several that came to pass. One is we have some software that can steer us in to do all the path planning for two satellites that are traveling at 7 kilometers per second, make a nice, safe docking maneuver. And then we also have some hardware that makes that soft capture possible. And so all of this we put on a vehicle we call the Otter Pup. And why we call it the Otter Pup is because our full servicing spacecraft is called the Otter. And this is a smaller version, about the size of a microwave, that has all of the technology on board. And so by being the smaller version, that's the demonstration mission that comes first. It's the Otter Pup. And so Otter Pup was launched back in June of this year aboard a SpaceX rocket up to a special orbit called Sun Synchronous. But this is just extra detail for those that are space curious there. And for us, what that mission was supposed to do and is going to continue to attempt to do now that we've crossed this major threshold that we'll talk through is go chase down another spacecraft, find that spacecraft and actually approach it and then gently grab and attach to it. And this is an incredibly hard thing to do in space. And even more so, it is hard to do with some of the other things that we're trying to do at the same time. We're trying to make this an autonomous spacecraft that can do it on its own. And we're also doing it for the first time ever in spaceflight with exclusively electric propulsion, which is just a really, really soft level of propulsion that just kind of pushes you almost like the weight of a piece of paper on your hand. But if you do that over the right time and over the right time scales, you can actually go and make these big maneuvers. So all of that is what Otter Pup is going to go and hopefully show. Now, after we launched, we got some unfortunate news that one of the vehicles we were riding on had an anomaly, and our combined stack, both us and them, spun up to hundreds of degrees per second, which is incredibly fast. That's about 100 times what we should be spinning in a normal operational state. We were able to separate successfully thanks to some of the contributions from their team to make sure that we were off, and then began a recovery process. How do we slow down this spacecraft called Otter Pup down from hundreds of degrees per second back to around 0 degrees per second or 1 or so degrees per second so that we can go on and do the rest of this mission? And that's really what Starfish has been putting a lot of attention to over the last month or so, or 2 months, is slowing it down. And we were able to, as a team, build up a set of algorithms, run a set of tests, and actually ultimately totally take out all the rotation rate, which is incredible in its own right. This is not a common occurrence to be able to recover a spacecraft in this way. And we also did it in some pretty novel aspects in terms of the software, but it really buys us a second chance to continue the mission here and go and try and dock with another spacecraft.
That's amazing. So I have to back you up. And I told you before we started, I'm a
Yeah.
real space nut, and I have never heard the term sun synchronous orbit. Can you give me a quick layman's definition there?
Yeah, there's a series of orbits that are kind of highly prized for certain aspects. Sun synchronous is just what we call a highly inclined, meaning it travels over the North Pole, then over the South Pole, and then over the North Pole, and so on. So equatorial would be if it was just going around the middle of Earth. Sun synchronous goes up above. It has some better properties for Earth imaging satellites and some others, which is why we were able to ride on a rideshare mission where ourselves and 70 other spacecraft were all going to the same place. We all wanted to go to this orbit. And so a rideshare mission could take us all to this special orbit.
Now, you you and your team also, as I understand it, used the Earth's magnetism, the Earth's magnetic field to slow this spin down. How
Yes.
does that work?
That is a great question, and maybe I'll answer this in three different levels of complexity. So at a high level, the first thing that we're doing is we are just pushing against Earth's magnetic field. And if we've ever seen a picture of a bar magnet, like the North Pole and South Pole, there are these little lines that kind of connect the two. Earth is the same. It has these lines that connect. We can also create a magnet on our spacecraft using electricity. And if those two magnets interact, they push against each other. And our little spacecraft is not going to push the Earth anywhere, but the Earth can push our little spacecraft pretty well. And so we can actually time it in such a way that we're pushing counter to our spin. It's almost like if we were spinning around in the water and we stuck our arm out, it would slow us down. We're trying to do the same thing here. And so the way we actually create that local magnet on our spacecraft is by passing current through a coil of wire. And that coil of wire is an inductor, or as we like to call it in the space industry, a torque rod, because when we put electricity through it, it creates an interaction with Earth's magnetic field, which creates a torque. And all that is just a resistance to the spin here. We can actually slow ourselves down that way.
Unbelievable. So when it was in this spin, was it potentially a fatal spin that could have sent the thing hurtling back down to Earth, a deorbit, or just something you had to stop while you were still up there?
Yeah, that's a great question. So we are in an orbit altitude where we would have come down and lost the spacecraft over time had we not recovered it. While we were spinning, we actually had less control of the spacecraft than normal. We were able to still maintain communication with it, but we cannot activate some of the normal systems that we would use to control the spacecraft. And so this was just one of those control systems that was still viable at the time to be able to slow it down. And that's why we had to go and actually do some of the math to figure out how we would control it with a limited set of actuators, which is just like these torque rods, and a little limited set of sensors. We didn't have all of our sensors turned on either because some of them don't work at those really high rotation rates. And so that was a lot of the challenge that we were able to overcome, was how do we use a limited set of control and a limited set of sensing to actually go and perform the mission here. This is a rather rare occurrence, one, to have a spacecraft go spin that high, and even more rare to be able to slow it back down after it spins that fast and slow it down as quickly as we were able to do so.
Yeah, it makes me think, and I know you're familiar with it, the Neil Armstrong mission where they were testing, in Gemini, the ability to dock, and they had that terrible spin going, and
Exactly.
how he managed to stay conscious during that is a miracle in and of itself, spinning so rapidly. But it is dangerous for a
Mhm.
spacecraft, whether it's manned or unmanned, and so I get that it's a major problem. And as I understand it, and please correct me if I'm wrong, another part of the problem is you needed it to stop spinning so that you could aim the solar panels and keep the thing powered, right?
That's exactly right. That's exactly right. So the way a spacecraft stays alive is we get enough power on the solar panels to run all of the systems on board. And as we were going through this recovery process, there were times where our solar panels were not pointed at the sun. And because we were still spinning, we had less ability to actually go and turn it back towards the sun. And so there were a couple of times that we actually dipped through and the spacecraft shut itself down or browned out for a while and then came back to life again when it got a little bit more light on those solar panels. That is a very nerve-wracking experience to go through that. It's very stressful to lose connection with your spacecraft while it goes into a low power state. So that's why a lot of the time was spent making sure not only as we slow it down, are we pointing ourselves in the right way? And that gets easier and easier as we get closer and closer to the finish. Now that we're in a nice stable state, all of the control algorithms that we've written in the past and kind of continued spaceflight experience says it's very easy to point it over. But yeah, during the time, that was a lot of the challenge that we were overcoming, was making sure that as we went through these operations, we were using as little power as possible. So turning off unnecessary systems, and then also trying to tilt ourselves just a little bit more towards the sun and get a little bit more light on those main solar panels.
So we're stable now, right? You've got it aimed where it needs to go. It's not spinning
Yep.
out of control. You're in good shape.
Good shape as far as we know. I think this is what's definitely true for spacecraft. We're not designed to spin at this rate, but we're taking a step back and saying, yes, as far as we know, the spacecraft is healthy. We've given ourselves a second chance to go do some of these meaningful steps. What comes next for us? We are going through a series of steps now where we're checking out the different spacecraft subsystems. We're going to go make sure that the radios are still working well. We're going to go make sure that the thruster still works well. We're going to go make sure that some of our control systems all work well. These are systems that normally would have been turned on in a regular cadence had we not been spinning. But now that we've gone through a spin, we have to go and double up and make sure that they didn't get damaged during the deployment process. We're not jeopardized by the high spin rates. And so it just requires a little bit more diligence on our part now to check out some of these other subsystems after recovering the spacecraft. So far as we know, it's still in a good place, and we're going to go do the diligence here to check out those systems. Should they all be working and functional, then it opens up the next opportunity for us to go and chase down another spacecraft and actually go do the mission that we originally planned on doing, which as a shameless plug, we put out a 2-minute video on that back in November that highlights how ambitious this is and what we're going to try to accomplish over the course of this multi-month mission.
Is that the YouTube video that I saw on your website?
That's exactly right. That's the
Well,
YouTube video that's on the website there.
Guess what I will be embedding when I post this story on the web. I want to make sure that people get to see that, because I've seen it and it's pretty amazing what you're going to do. Now, let's just say worst case scenario, fingers crossed this isn't what we're going to have, but let's say there is some damage and you're unable to make use of the Otter Pup vehicle that's up there. Is there a backup? Did we send another one up?
It's a great question. So part of what Starfish is trying to do is go prove out some of the core technologies that we're doing. We have a number of ways of doing that, and the space industry in general has a number of ways of doing that. One of those ways is a lot of what we call terrestrial testing. This is just testing on the ground on Earth here. We have actually tested a lot of our flight systems and even our capture hardware, which is the grabber out front, in vacuum chambers or on air-bearing test beds, which is just where you're almost like a maglev or an air hockey table where you can simulate all of these things in space. We are still doing that testing actively right now. And so that complements what we're going to see in space. We have lots of simulations that aerospace industry really relies on heavily to go improve some of these things out. We would love to see Otter Pup, this one that we've launched, go and succeed in this mission. If it doesn't, there will probably Starfish will find its way back to orbit one way or another to go and continue testing here.
Excellent. So let's say we are able to move forward, and you've touched on it a little bit, but let's talk about the potential of what the full-size Otter, once it's ready to go, can do, because it sounds like, we're going to be able to extend the life of satellites and clean up the debris, which is an important one because, as we've seen the International Space Station get hit with stuff and take on damage. There's a company up in Marysville that wants to build space station modules, so there will be more up there, and they're in danger of being hit with the debris. But it's not just about cleaning up debris; it's about not having to send NASA up every time like they used to when a satellite needs repaired. I was fortunate enough to get to talk to Jeff Hoffman, who, along with Story Musgrave, I see you nodding your head, did the first Hubble repair mission.
That's
I
right.
remember that specifically because Dr. Hoffman, his brother, worked with my mom, so she got to meet
That's
him
super
one
cool.
time,
Yeah.
which was awesome. And then years later, I got to chat with him right before they were going to do the final Hubble mission, just to get his perspective. But those are important functions because we're sending more up. SpaceX, you guys are working with SpaceX. They're going to be sending a lot more stuff up, and it's better to keep it working as long as you can, isn't it?
Yeah, I think you're touching on a lot of great threads. Let's pull a few of those. One is why we were able to even do an Otter Pup in the first place, which leads to an Otter, is we are trying to find an economically viable way to do life extension. As you highlighted, the Hubble telescope was extended 5 different times. We had multiple missions to go up, swap mirrors, swap cameras, swap out the solar panels. All of these things helped extend the life of one of the most incredible telescopes we've ever launched into orbit. Those each cost $1 billion to go do. that's not something that we can do on a commercial scale that you're already describing, right? That we're going to be continually launching these space stations, and that's, we're going to continually launch these satellites at scale. We need to find a way that's economically viable there. One of the things that was incredible about Otter Pup was we were able to do so on less than $8 million in venture capital as a company. Go and deploy a full mission that can go rendezvous and dock with another spacecraft, or so we plan to hope demonstrate. What that means for the Otter is that that same core thesis of being able to build complexity into the software, being able to rely on our software, which helped us detumble a spacecraft and is also going to help us dock spacecraft, is going to make something the Otter size, which is about the size of a washing machine, or 200 to 300 kilogram range, or ESPA is a specific term for the launch vehicle folks. That size spacecraft, which we call the full Otter, is actually going to be able to go do this life extension mission at a price point that makes sense for customers. It'll make sense not only for the big satellite geo operators, but potentially the LEO operators that are launching internet constellations or Earth observing constellations to help remove their old satellites or keep their orbits clear. And that's why we have kind of focused on some of these core technologies that we're building at Starfish. That's why the Otter Pup is taking us towards that full Otter. And that's why the full Otter on that small scale the size of a washing machine can push around the size of a school bus. And so these big geo satellites that are the size of a school bus and need a few extra years of life, we can grab onto them, move them back to the right orbit and keep them there so they can keep flying. And hopefully in the future, as you start to, elucidate where we have got space stations that are coming online and more launches and more launch vehicles, there's just going to be hopefully an ever increasing need to maintain our orbital environment, and even more so start building and assembling and expanding our capabilities on orbit beyond what we've done so far.
Absolutely fascinating. I'm just mind blown by this whole thing. Now, another thing, as I understand it, and again, correct me if I'm wrong, but the space tug that was supposed to work with Otter Pup and move it around, that I guess didn't survive the spin out. So now you don't have a vehicle to practice docking with. What's the plan there? What are you going to use?
Yeah, it's a great question. So, part of the way we constructed our hardware on board Otter Pup as well as Otter is we have a capture system called Nautilus. And as you can tell, we're really doubling down on all the nautical themes here at Starfish. What Nautilus does is it's a capture system that uses electrostatics, which means we can actually grab a variety of different spacecraft surfaces. That means insulation, solar panel material, aluminum, whatever kind of surface space is already on spacecraft designed for their own mission. What that does is it provides us an opportunity, because as part of our rideshare mission, we were launched with 70 other spacecraft that are going and doing demonstration missions, big commercial missions, which means there's a plethora of other spacecraft up there that might be good candidates for us. And because our technology allows us to grab any type of spacecraft, we can actually go and engage with all of those other satellite operators and try to find a partnership where we would go chase down one of their spacecraft instead of what we originally had planned. That is incredible if we're able to pull that off, because it really does validate what we're trying to build in the Otter as well, which is an ability to launch into any orbit and go and support, provide a service to any spacecraft that is in that orbit. And they don't have to change their design for us. We go and actually dock with what they have existing. And that's what we're going to potentially have to go prove a little earlier than we expected here, because we're going to have another spacecraft that was never designed to be docked with a Starfish spacecraft here, and we're going to go capture it.
So one of the other things I keep thinking about, Trevor, is when you're talking about two vehicles meeting in space, I'd like the perspective I like to put it in is, if two kids are standing on either side of a house, and both of them, let's say, have a golf ball in their hand, and they throw them over the roof, being able to, the two balls to strike each other. I mean, that's how crazy it is trying to get two objects, specific objects, together in space. So
Yes.
for me, you kind of have to dumb it down a little bit, but what's the trick there?
Yeah, it's a great question. We have lots of analogies for ourselves because it's such a crazy problem to solve. I've used in the past, you have two race car drivers driving down a track and they're trying to give each other high fives, right? This is similarly what we're trying to do in space, except rather than going several hundred miles per hour, we're going several thousand miles per hour at the same time. Part of the trick, and that's really what we've baked into our software that we call Cephalopod, again with the theme, this is our guidance and control software that does path planning. And so we actually set up a series of maneuvers where we're firing our thruster at a particular orientation at a particular time to almost bring those two spacecraft ever closer and come in at the right angle, at the right time, with the right velocity. These are all things that we have to do, which is, again, just trying to make that high five at the right place at the right time. Part of the reason we go and rely on our software is because we can simulate that well. We can validate that against our operations in space. We can trust the math that we've developed and implemented and actually scale that up to an entire constellation of otters, where as soon as we get it to work with one spacecraft, we can start using it on multiple spacecraft. And then you almost get to a place where you have space Uber or space Lyft, where you can actually send a fleet of otters up into orbit. You can send an otter, hey, this spacecraft needs you to dock with them. It can autonomously go over, navigate to it, capture that spacecraft, and send us a message back saying, I've docked. What would you like to do next? And that's really what we're trying to build into. And that's how we've gone about this, is using some of the mathematics around astrodynamics, which is kind of the field of this mathematics and how the different spacecraft move together and all these arcs and paths, and trying to just make those arcs intersect at the right time using our thrust control. And so that's really how we've thought about the problem. That's why we've built Cephalopod, as we've actually been able to highlight just in recent weeks as well. Cephalopod got some continuous funding from the Space Force to go and further it, because it is such an applicable capability, not only to what we're trying to do, but so many other fundamental missions here.
Excellent. Space Force is involved. That's fabulous. So that I do have a question when it comes to regarding that when it comes to cleanup, but let's talk about debris cleanup as well, because it's not just repair. Sometimes you're going to be taking stuff out of the way. I mean, is the idea for, let's say, like otter to grab onto something and orient it in such a way that it just dives into the ocean? I mean, what's the plan there?
That's a great question. Yeah, for some of the debris removal, that is what we are thinking. There is an action where a whole constellation or a really densely populated orbit where two satellites might hit each other. We would go grab one of the spacecraft and push it down or slow it down so that it dips further and further into the atmosphere. And as it does, it'll slow itself down and then burn up, or hopefully not hit the ground. We actually design our satellites to burn up in the atmosphere on reentry, much like more like a meteorite would, rather than actually make contact with the ground.
Okay, so then that leads into my next question. And it's just something that occurred to me as I was thinking about this. Any concern that the military might want to latch on to this technology and, go up there and start using it to grab onto Russian and Chinese spy satellites and like fling them down into the ocean?
That's a great question, and I will be delicate with the answer here, right? Because historically humans have found ways to weaponize things. But that aside, I think part of what Starfish was founded on and part of what our intent is here is to go create a commercial future and a business future for space. We want humans to go explore the cosmos, and we think actually many of the use cases, even in the near term, are those where commercial companies can benefit from it. Life extension in GEO, removal of space debris in LEO, starting to use this for assembly of telescopes or maintenance of space stations. We think that that's really where a lot of the application can happen. And naturally, you can imagine that there are the same kinds of technologies that are used to do that could find their way into defense applications. But for us, we're trying to make sure we're also doing the commercial elements as well.
Very good. And you hit on something else that I meant to mention as well. It's not just repair and removal. There's the potential to actually build things in space autonomously. Like you
Correct.
don't even have to have humans up there doing it. Send the parts up, put it together.
That's right. Yeah, it gives me chills every time watching the Otter Pup video that we put out, because we do, in fact, fly in and put a mirror into a giant telescope that's a little bit bigger than James Webb. And so those are the moments that I think get us excited and get us motivated to go and and work through the challenges like we have on Otter Pup and work through building this full Otter spacecraft is because if we can go and now take these next few amazing steps and try to do this really ambitious mission, it does open up that future for assembling structures that previously were just not able to put on orbit.
Fabulous. Trevor, what have I missed? What didn't I think of?
There are always so many things to talk through in space, but I think there's a couple of things that just to reiterate through our conversation here. One is the Otter Pup mission is an exciting one to be a part of here, and for us at Starfish to be pushing forward. This is a mission we'd love for people to follow along with and join us on the journey for. There are a lot of things that still are challenges to overcome. We have to go do one of the most ambitious missions that have been done in spaceflight and go dock these two spacecraft. A lot of things could go wrong. A lot of things could go well. That's why we're on this journey here. And really amazing for us to be afforded a second chance there as we at Starfish were able to go and recover a spacecraft from a pretty incredibly challenging situation. And even those in the aerospace industry have looked at this and said, this is incredible. And so what a great step for us to go and take here. And then the next thing is always true is this is an industry built where the rising tide raises all boats. I think there's a notable aspect that as we highlight even those that you have in the Seattle area that are doing some incredible space things, but also our partners that have helped us in the journey here to both build and launch and explore what Otter Pup can do and what Otter will do. I think that's a good recognition for all of us in the space industry that it really is many partnerships that help make things happen.
Fabulous. Can't wait to see how it goes. Trevor Bennett with Starfish Space. Appreciate you taking the time to join us.
Yeah, thank you. Appreciate the time here as well.